Well, you might think that things were so similar in this particle in a box and in higher dimensions that in 2 dimensions that what really is new, and there actually uh, does occur some interesting new phenomena when you go to higher dimensions that just do not exist in one-dimensional quantum mechanics. And one of those is degenerate energy levels. Let's look at our two-dimensional particle in a box again. But this time I won't have A and B different, but I'll have them the same. So now the width and the length are identical, so it's really a particle in a square box, not a rectangular box. And that's pretty easily done. You just, everywhere there was a B in the earlier, I'll substitute an A for it. So we had, this was the X one, that doesn't change. But the Y, this was a B and a B here, but I changed those to A's. And so now we've got the wave functions. The energy is interesting too. And that ordinarily I had this with a squared, and here was a B squared. And now I've got the same factor, so when I replace the B with an A, I can factor out this common factor, and I just get the sum of these integers squared for the energy levels. And what that allows to happen is, I'll just note that if N1 is some particular value, say L, integer, and N2 is another particular value, call it P, then I get exactly the same energy if I have those two switched, if N1 is P and N2 is L. So the energy of the LP is the same as the energy of PL, it's just this value. But the wave functions are totally different. LP, I get the L on this term, which has the X in it, and I get the P with the Y on this term, which is with the Y in it. Okay? And the PL, the P is with the X, and the L is with the Y. And so pretty clearly those are not the same functions, okay? Because they differ in both the X and the Y functions. And if you were to plot them, you'd see totally different functions. For example, let's just look at a particular example of the case where L is 1 and P is 2. Okay? Then I can write these two wave functions, in this case where A is equal to B. I can get the energy for both of them. The E12 for this wave function is just this, but it's 5h squared over 8m a squared. And this wave function here, 2,1, well, yeah, the order's different, but it still turns into 5. So I get exactly the same energy for this state as this state. Same energies. But again, the wave functions are totally different because they have the 1 and the 2's occurs with the sine and cosine. Or the sine and the sine y and the sine x term. So psi 1, 2 is this. 2 over here with the y, the 1 with the x. And psi 2, 1, the 2 is with the x, and the 2 here is with or the 1 is with the y. So you can see they have different wave functions, but they have the same energy. And when those situations arise, it's said that such states are said to be degenerate. They're degenerate in the energy. They have energy degeneracy. Totally different wave functions, totally different states, but they just happen to have the same energy. So sometimes it can happen that there's more than one. In this case, the one generally defines what's called the degeneracy or the degree of degeneracy of the energy state. And that's simply the number of different independent wave functions that have exactly the same value for the energy. So in this example above, I've got two different wave functions that have exactly the same energy. And so the degeneracy, usually represented as G, or G sub E for the energy state, is 2. Is the degeneracy, or the degree of degeneracy. Well, if you think about it, the reason we have such a degeneracy occurring is because of really the high degree of symmetry that we have. Instead of having a rectangle where A and B were different, we have a symmetry of it, really total symmetry. We have a square. Mm-hmm. So one way that degeneracy can occur is when we do have a highly symmetric situation. Another way can occur is that if A and B, the length and the width, are just such that their ratio squared is the ratio of a couple of integers squared, L and P. And if that's the case, then I could certainly solve this for B up here. If I solve this equation, for B I would get P1 L1 times A. And then I could substitute those in for B here, which I've done. And then I can factor out an A, but this L squared over B squared, A squared over B squared, is L1 squared over P1 squared. And so the P1s go out, and I get 2L squared here. So it can happen if the ratio of A and B, the length and the width of the box that they're in, just happens to be the same as a ratio of some integers, then one can get a degeneracy as well, that two states would have exactly the same energy level. For example, let's suppose that A squared over B squared is that B is 5 times the length of A, and so I get this A squared over B squared is the ratio of 1 squared to 5 squared. So, and then I can write A and B then as 5 times A. I can write the state 1, 5 is going to be 2 over A. Okay. The sine function, these go out, and likewise over here, the same quantity, and you find that the energy levels, the states are the same. The energy levels are well. This first one is 1 and 5, so that becomes 26. The second one is 5 and 1, so that becomes 26 as well. And so the E15 is E51, simply because these ratios of A's and B's turn into a possible ratio of integers, squares of integers, really. Yeah. Well, such a degeneracy occurs because of really a special relationship between the A and the B, the width and the length of the two-dimensional box. Now, ordinarily, we would be considering a problem in which we maybe measured that or fit that to the best curve so that A and B are sort of whatever they turned into be from the physical situation. Or maybe we designed it in an engineering mode and we just designed an A and B. But in the case of it just naturally occurring, then it's kind of an accident that these two constants that define this well are in a commensurate ratio with one another, so that you get this degeneracy occurring. And as a result, these kinds of degeneracies are sometimes called accidental degeneracy. In general, in quantum mechanics, in more than one dimension, you can get two kinds of degeneracy. You can get those that are caused by symmetry, so having a highly symmetric situation, and you can also get them when the physical parameters of the system sort of conspire to in an accidental degeneracy situation, so that you can get ratios that will display these degeneracy effects.